So today we're going to be going over conditional probability. So conditional probability is just asking the question, the probability of an event A given that B occurred. So we denote this by saying right here, the probability of A with this line would be given B. And so this is defined as the probability of A intersection B times the divided by the probability of B. And this can be rewritten as the multiplication law of probability, as the intersection equals the probability of B times the probability of A given B. So let's see if we can get that formula into practice by seeing a simple example. So going over here, we have a matrix of, this is students, and we're trying to see whether these students enjoy or dislike going to the dentist. And this is segmented based upon what type of school they're in, so elementary, middle school, and high school. So going through this example, let's see. The probability of A, which is the probability that they enjoy going to the dentist, would just be the summation of those who enjoy in the matrix. So we'd say 0.12 plus 0.8 plus 0.5. So this is 0.25 or 25% of the students. So now let's see if we can use this information to try and solve the conditional probability. So the probability, let's write this out. So probability that a student enjoys going to the dentist given they're in elementary school. So as it is, probability of A given B equals probability of A intersection B over the probability of B. So we know from here that the probability of A intersection B is simply just 0.12. So we can input 0.12. B is in elementary school, so we would see that it's 0.12 plus 0.28. And this would give us 0.12 over 0.4. We think that whether they enjoy or dislike going to the dentist is it independent or dependent on education level. And so we'd see that since the probability of A does not equal the probability of A given B, that these events are dependent. Because otherwise, if they were independent, it wouldn't matter. If B occurred or B didn't occur, they would need to be the same. Now we'll get into a different idea called total probability. So again, we're sticking to a sample space containing two events, A and B. So again, we have A and B. And so given these two events, the event A can occur either when B does occur or B does not occur. So for example, A is the union of A and B complement, as that's the total probability. So for example, we would say, by definition, the probability of A equals the sum of probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. And this will become very useful in the next step when we talk about Bayes' rule. So getting into Bayes' rule now, which has to do with conditional probabilities. So we want to suppose that two events A and B can occur together, but before observing the event, we know the probability of B, which we'll call the prior probability, our prior knowledge on the event. And so when we know the two conditional probabilities, these two, we know probability of A given B, then probability of A given B complement. The probability of B can be updated when we observe the status of A. So for example, the probability of B given A equals the probability of A and B over the probability of A. And we know here that the probability of A and B equals probability of A given B as the probability of B. And using the law of total probability that we talked about before, we can see that the probability of A is equal to here. So the probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. And therefore, we'll connect all of these things together to get our new solution to the question above. So to the solution to here. So we would say probability of B given A equals the probability of A given B times the probability of B over this total probability here. So probability of A given B, PB plus PA given B complement times B complement. And so this is equal to what we spoke about in the beginning, probability of A, B over the probability of A. And this is the total probability. Less invasive procedures are used to screen or predict the presence of a disease or condition. So for example, mammograms or a PSA test or blood pressure tests. And so we're trying to get an accurate test, which means they predict a disease with a high probability. And so a lot of times they'll use Bayes' rule, which we talked about before, to identify the efficacy or accuracy of these screening tests. So for example, let's let A be the event a person tests positive. So test plus equals A. And we'll say B equals they actually have the disease. Definition sensitivity. So sensitivity of this test we're using is the probability of the test showing a positive result given they actually have the disease. So the probability of A given B. So test positive given they have disease. So this is the probability that our test is accurate for positive tests. And specificity would be the probability of A complement given B complement. So the probability you test negative given you don't have the disease. So conversely, we have the predictive value positive and the predictive value negative. So the PV plus, or predictive value positive, is the probability a person actually has the disease given they have a positive result. So it'd be the inverse of here. So let's get a red pen out. Let's say probability of B given A. So the probability that they have the disease given they already tested positive. And PV negative would be the probability they do not have the disease given they tested negative. So this matrix gives us an idea of what we're trying to solve with these positive values, PV negative, PV positive, sensitivity, and specificity. So here, the matrix will show there's a positive test and they do have the disease. So we have a true positive. And conversely, we have a positive test but no disease, that's a false positive, and so on and so forth. So our sensitivity value here, which we're calculating before, is simply the sum here is simply the true positive over a true positive and a false negative. So the entire value of diseased people. And conversely, for no diseased people, to get the specificity, we would take a true negative value here and divide it by the sum of a true negative and a false positive. So it's the entire disease community. So that gives you an idea of what we're trying to do with these tests. Let's take the example here that we're trying to solve for a rare but serious disease. So we find this disease is present in 1.4% of the population. So not very high, but a decent amount. However, we're not finding that these medical tests are completely correct, but they're very good. So we have a high sensitivity of about 99.5%, and also a high specificity of 98%, which are denoted here, here, and here. And so let A be the event that the test is positive that a subject would take, and also B, that the subject has the disease. So let's try and answer the question 1. What's the probability of A? So if we think about this from before, we have all of the information here. We have the specificity, we have the sensitivity, A and B, and the prevalence. So we know that the probability of A, using the law of total probability, is just simply the probability of A given B times the probability of B plus probability of A given B complement times B complement. So let's fill in the information. We know the probability of B, which is the prevalence of the disease, equals 0.014. And then the inverse, or B complement, is just 1 minus, which would give us 0.986. In addition, we know the probability of A given B is actually here. It's our sensitivity. So we already have that number, 0.995. And similarly, we have the probability of A complement and B complement is the specificity, so that's 0.98. And the complement of this is simply the probability of A given B complement, which is 1 minus 0.98, which is 0.02. Give us 0.034 or 3.4%. So this would be PA, which is the probability of a positive test. So if you think about this for a moment, let's go back to our notes. Probability of B given A is just our predictive value positive. So you want to come to our chart here, and we would see that this is just simply the value of the true positive over the true positive plus the false positive. So we're just trying to evaluate that question. So let's go back to the notes to solve this problem. And so right now we're going to actually use Bayes' rule. So let's think about all the way back to here. So let's go Bayes' rule. And so we'd have that the probability of B given A from before is the probability of A given B times the probability of B over probability of A given B, probability of B plus the probability of A complement plus the probability of A given B complement times the probability of B complement. And we know this because if we take a step back, actually, this is simply the probability of A intersection B over the probability of A. All those numbers from before. So we have A given B again is the sensitivity of our test. So 0.995 plus 0.995 times 0.014. And similarly from before, we have 0.995 times 0.014 plus 0.02 times 9.986, which gives us 0.414 or 41%. So we can see that the PV positive is 41.4%. So this is just something to think about because the probability of having the virus is only 41.4% given you test positive. So finally, I want to talk about the relationship between sensitivity, specificity, PV positive, and PV negative. So these are all intertwined in the formulas of Bayes' rule. So if you want to do the probability of PV plus, that's the same as the probability of B given A, which is the same, again, as we proved before, as the probability of A given B times the probability of B over the probability of A given B, probability of B plus probability of A given B complement, probability of B complement. So we have here the sensitivity there. Here we have the prevalence. This is the same over here. And then we also have down here 1 minus specificity and the inverse of prevalence. So in summary, we're just explaining here that if a decision is based on only the test result, then we're really looking for the highest predictive value positive, the better. But like we've seen in this last example, the predictive value positive doesn't depend only on the sensitivity and specificity, but also the prevalence of the disease. If the disease is not very prevalent, it could be very difficult to predict, and that's what the numbers will show us. And so in a lot of medical research, the Bayes rule can really help update the probability of the patient's disease status given the test results from the knowledge of the sensitivity, specificity, and prevalence. And so other things that Bayes rule has been applied to is identifying spam, discovering defective medical devices, and other things.